Inviting Dr. Mohammad Yan.
इनका नाम क्या है?
Okay, I'm here. Okay.
अरे यार
Good afternoon, Professor. Is it audible? Dr. Mohammad Yan.
Yes, I'm here.
Yeah. Please start your presentation.
Okay, I start.
Dr. Pong Yang Ring has got his degree PhD from Institute of Applied Taiwan University in Applied Mechanics in 2009. And presently he is working in Industrial Technology Research Institute Center for Measurement Standards since 1989. He is working in the area of high pressure gas flow measurement and design. Thank you, Professor. Just please start.
Share your slide.
Okay.
Sir, please, sir, you can share your slide.
Dr. Pong Yang. F-O-N-G R-U-E-Y.
नमस्कार मैडम, बस बढ़िया।
टेम्परेचर बढ़वा दीजिए, बहुत ठंड है।
ठंडा हो रहा है? ओके,
लोग बीमार हो सकते हैं।
नहीं बोल देता हूँ, हाँ बोल देता हूँ।
प्रेजेंटेशन का शेयर कर रहा है। हाँ सर, एक सेकंड। हेलो, अरे भाई थोड़ा सा एक आप यूनिट बंद कर दो, थोड़ा टेम्परेचर बढ़ाओ, ठंडा हो गया। मतलब क्या है नेम क्या अल्फाबेट में ये इंग्लिश अल्फाबेट है या हाँ टेम्परेचर बढ़ा दो। नहीं
ऑन करने का ये है, बंद करने का उसको वहीं टेक दिया गया। इसको वहीं रखता है।
इंग्लिश में नहीं यहाँ किसी और से जूम।
Dr. Yan, is it possible to share your slide, please? From your
Yes.
side?
Pardon?
Because it is difficult to search your presentation.
Pardon?
It is difficult to search your presentation. Is it in Chinese language or which language? Because we are unable to locate in the email your presentation.
Yes. Now I presentation now. Okay.
If you have, you can start your presentation if you have.
Oh yes, I have a presentation because I have recorded the entire briefing in advance, so I will play the video first and ask a question after the broadcast. Thank you.
Professor, your video is not coming. Please be online.
Okay.
Yeah.
Okay.
सर 10 मिनट हो गए तो उसमें लिखा है जापानीज है चाइनीज क्या है
रिकॉर्डिंग
Sir, is it in Japanese language or which English language?
Sir, ask him to share again his PPT.
Can you share please your PPT? Professor Yan,
Pardon?
can you share your presentation please? It is in Japanese language or Chinese? In which language it is?
Chinese.
Chinese.
No,
Uh,
PPT एक बार देख लेते हैं.
Please open your PPT.
okay, I now
So,
open.
And share it.
Please show your face also, please. Please share your PPT also.
Okay, because our presentation is the have a record for the entire briefing in advance. So now I play the video first. Okay. Now
Do you have presentation?
yes, I can present.
Yeah,
I
please.
can present it. Okay.
Professor Yan, is there any problem? Professor Yan?
Yes, I'm here.
Yeah. Is there any problem?
Yes, I'm here. But,
Are you unable to present? Is there any problem?
mm,
Excuse me, Professor Yang, this is Mr. Ramlin.
yes.
Can I ask you, on your computer, towards the left-hand side, when you move the mouse, there's a red circle, there's a camera, and then there's a microphone, and then there's an up arrow. Can you please press the up arrow with your mouse and then share the desktop? And then
Okay.
when we can see the desktop, could you just double click your video and then we'll watch your video. So you don't have to talk from scratch. Just try and share your desktop and then play the video and we'll watch your video, if that is in order. I apologize, Dr. Yadav, for interrupting. I yield the floor back to the colleagues at NPL.
Okay. I can try another.
Professor Yan,
Oh.
can we ask another speaker? You can make preparation after 15 minutes. Is it possible after 15 minutes?
But
We can ask new speaker because if it is taking time, then we are already going late.
I can present this presentation repeater. Okay.
After 15 minutes?
Yeah, I presented the. Can you hear the my presentation? My
No.
presentation. Okay. Can you hear me? No. Can you hear me? My presentation.
No, video is not.
No video.
No video. Oh.
So इनको इनके स्क्रीन पे क्या दिख रहा है इनको सर? नहीं
I can try this.
स्क्रीन
I
पे
can try this.
क्या ऑप्शंस दिख रहे हैं?
What are the options in your screen?
Okay.
Can you send your presentation in our email again? We will share that.
Yeah.
Reliable calculation models of ultrasonic flow meter for high pressure gas flow traceability. This paper has been organized in the following way.
It's okay.
Yeah.
First is introduction.
Yes, I'm here.
and circulating high pressure gas flow calibration
I'm here.
equipment.
Yeah, it is okay.
Then multi-variable regression model establishment. And the result and the discussion and the conclusion. This paper first gives a brief overview of high-pressure gas flow calibration equipments. The high-pressure gas flow standard system of the National Measurement Laboratory is a primary system.
Mr. Chairman, can you hear me my presentation?
It is okay now. It is okay now.
It's okay?
Yeah, it is okay.
Oh,
Please,
okay.
please 15 minutes.
The
Please try to please
operating gas is high-pressure air with a pressure range of 1 to 60 bar and a temperature range of normal temperature with a minimum of about 10 degrees Celsius in winter and a maximum of 32 degrees Celsius in summer, flow range of 15 to 12,000 cubic meters per hour. Because this system cannot meet the industry's high pressure and large flow calibration needs, the Bureau of Standards invested in an expansion of an existing circulating system in 2019. The original circulating system with a pressure range of 5 to 55 bar absolute pressure, a temperature range of normal temperature, and a flow rate range 125 to 27,500 cubic meters per hour. The transfer standard between primary and the circulating system is rotary meter. This slideshow illustrates the new circulating equipment. This figure is the system flow chart of the calibration equipment. This equipment uses two high-pressure blowers to drive the high-pressure air inside the closed circulation pipeline to circulate continuously. The maximum operating pressure is 55 bar. The maximum actual volume flow rate is 800 cubic meters per hour for Holden and 2,000 cubic meters per hour for Antigua. Because the high pressure blower is a heat source, a heat exchanger is equivalent to maintain the fluid at a constant temperature close to the atmospheric temperature. At the maximum actual volume flow rate and working pressure, the fluid temperature does not change by more than 0.2 degrees Celsius within 5 minutes. The maximum uncertainty should not exceed 0.25%. The standard components used in this equipment are 2-inch rotary meter and 2 6-inch ultrasonic flow meters and 1 8-inch ultrasonic flow meter is used as a check standard. The procedures used for traceability calibration are as this table. Step 1 is a 2-inch rotary transfer standard, was calibrated by sonic nozzles of primary standard. Step 2 is 8 2-inch rotary meters were calibrated by transfer standard at circulating equipment. Step 3 is 2 6-inch ultrasonic meters were calibrated by 8 2-inch rotary meters at circulating equipment. Step 4 is one 8-inch ultrasonic meter was calibrated by two 6-inch ultrasonic meters at circulating equipment. Step 5 is two 6-inch ultrasonic meters were calibrated by one 8-inch ultrasonic meter at circulating equipment. The data regression in this paper is extracted from the calibration results of one of the two 6-inch ultrasonic flow meters and the calibration data of the third and fifth steps in this table are used. Solar data of 800 and 1000 cubic meter per hour are the results of the overlapping of these two steps. The challenges of standard units for this paper were as follows. There were many variables with big range, such as temperature for 10 to 35 degrees Celsius. The summer traceability data should predict the meter's performance in the winter, vice versa. Pressure for 5 to 55 bar absorbed. The traceabilities working pressures are only 5, 10, 20, 36, and 55 bar. We should predict meter's performance when the working pressure don't similar with these pressures. Flow rate for 125 to 110,000 cubic meter per hour. We should predict meter's performance at the non-traceability flow rate. In the future, we working through the may be different. The traceabilities results by using air should be used to other working fluids. What challenges is facing? In the field of flow measurement, only one parameter, Reynolds number, is usually used for regression or description of the characteristics of the flow meter. The regression curve must be predictable at all pressures, flow rates, temperature ranges, and even other working fluids. When variables become complex and the variables may be correlated with each other, the so-called multi-collinearity problem is formed. Our team has previously established various multivariable regression models of the flow meters. This study was developed in response to establishing a universal regression model of the ultrasonic flow meters errors for multivariable. The model should satisfy the requirements as follows. The difference between the regression values and the calibrating values was minimized. Avoid multi-collinearity problem such as red circles to show in the lower figure. Predict meters errors reasonably for large temperature difference between traceability data and the calibration data. As mentioned in the preface, when the flow standard was suitable for a wide range of pressure, temperature, and flow rate, the regression of the characteristic curve of the flow meter may have to consider the regression of multivariables. The approach of this paper was as follows. First of all, let's try to understand the principle of ultrasonic meter. According to the AGA report number 9, the ultrasonic waves emitted and also received by the upstream and downstream two probes. The relative velocities of the ultrasonic wave swimming in the fluid backward and forward are different. The entire flow meter is an empty pipe for the fluid. The basic dimension this parameter is the Reynolds number of the pipeline. Because of the design principle of the ultrasonic flow meter, the speed of sound of the fluid is involved. The Mach number associated with it can be considered as another dimensionless parameter. In the second place, we consider another method to determine the parameters. This figure showed the calibration results of the 6-inch ultrasonic flow meter. The calibration curve of 5 different working pressure were layered. So, in addition to the Reynolds number as one parameter, the pressure can be considered as another parameter. Above all, there are two groups parameters for analysis. One is Reynolds number and Mach number. Another is Reynolds number and pressure. Since we have decided two groups parameters, we could expand these parameters into various variables. First, carry out the permutation of two parameters. The first model or Reynolds number, Mach number, and Reynolds number multiplied Mach number. The third term of above items represents the interaction of the first two parameters, Reynolds number and Mach number. Continuing these three parameters set into a regression polynomial. Each parameter or polynomial includes -3 to 3 powers. The interval is 0.5 power. So each parameter has 12 variables. The total number of variables of 3 multiplied 12 equal 36. Second model for Reynolds number pressure and Reynolds number multiplied pressure. 36 variables were also generated by the same method of above procedures. In terms of filtering independent variables, linear model selection usually includes subset selection, shrinkage methods, and the dimension reduction method. The method used in this paper is mainly subset selection. The library using in this paper for filtering variables is Statistic Learning Library, which is called SPS as software package. It includes libraries such as forward stepwise, backward stepwise, and stepwise. We prefer the library was stepwise. Whenever a new variable is introduced into the model, it is necessary to check whether the independent variable in the model is still statistically significant and whether it can be eliminated. The brand and the model number of the meter under test used in this paper is SIG for SIG 600. The
Yes.
attached flow
Yeah,
meter.
please, somebody did 2 minutes.
Okay.
Please.
The diagnostic software can correct the influence of the pressure on the meter's geometry and the Reynolds number according to the input operating pressure. This paper does not consider the pressure correction function of the flow meter, and there is also no thermometer and the pressure sensor inside the flow meter. The pressure value P fix is directly fixed at 1 bar, and the temperature value T fix is fixed at 20 degrees Celsius, and then perform the calibration. This table showed the regression results of 36 variables, which were consisted of the 3 parameter sets: Reynolds number, Mach number, and Reynolds number multiplied Mach number. The variables were filtered down to 7 remaining. R square and adjusted R square were 0.9949 and 0.9947. This figure showed the calibration regression curves of 5 sets and 4 regression curves of non-working pressures at 15, 28, and 45 bar. The relative errors at the maximum pressure and the maximum.
Yes.
Yeah, please try to finish within 1 minute.
Oh, the time is not is all.
Just move forward,
It's,
please. Yeah, you understand because we are already running late.
Okay.
Yeah, please try to finish within 1 minute.
I conclusion. Okay.
Thank you.
Conditions.
Okay.
2 sets of regression model, Reynolds number, Mach number, and the Reynolds number pressure were combined to obtain highly accurate adjusted R-square values. Under the condition that the temperature of the working fluid was decreased by 20 degrees Celsius, the error shifting of these 2 sets of regression model parameters was all within a reasonable range. Similar to the multivariable regression model used in this paper, it was expected that all types of flow meters commonly used in high-pressure gas can use similar model analysis methods to obtain highly accurate universal multivariable regression curves. Thank you for your attention.
You use podium mount or collar mount?
Thank you, Professor Yan.
Oh, okay. Thank you. Thank you.
Now, on behalf of Chairman, I'm inviting Mr. Masayuki Yuka, who is presently working as General Manager and Global Sales Manager at Yokowa India Limited, Bangalore. This presentation from Industry IT. Mr. Masayuki, please.
F5
Thank you.
क्या हो गया?
Please try to listen to this. No problem.
प्रेजेंटर दे देना स्लाइड.
हाँ ओके
ठीक है. क्या कर रहे हैं?
वो ऊपर लाइन आ रही है क्या?
लाइन ऊपर की हटा दीजिए.
वीरेंद्र वो आ रही है. Click करो.
Good afternoon, everyone. My name is Oka, Yokogawa, India. I'm responsible for design measurement business in India. And I'm very glad to have this opportunity to present, Yokogawa's test solutions for especially for special measurement. I think schedules are very fast, but I can have some. Okay. Okay, let me briefly explain talk about our companies. We are Yokogawa, India, and then our counterpart in Japan is Yokogawa Test and Measurement Corporation, and that's dedicated to the test and measurement. And then some history. So Yokogawa established in 1915, so more than 100 years ago. So actually the Dr. Tanisuke Yokogawa started. So Yokogawa name is come from founder's name. So actually the founding principles, there are three things. Quality first, pioneer spirit, and contribution to the society. So here's the test and measurement network, global network. Worldwide headquarters is located in Tokyo, Japan, and then the regional office in US, Brazil, Netherlands, Bahrain.
Excuse me, colleagues, the audio has gone mute and I'm not able to hear anything. Thank you.
I can hear, right? I can continue, right? Okay. Okay, so our pressure business started in 1975. So after that, almost half centuries, we contribute pressure measurement in the various measurement fields. And from 1992, we start using our core competence, silicon resonance sensors. And then there are three categories, product categories: decimal manometers, controllers, and calibrators. So now we talk about some detail of silicon resonance sensors. So silicon resonance sensors is Yokogawa proprietary and self-developed and self-designed. This sensor is made by silicon single crystal using semiconductor process technology. And there are two vibrators inside, and the pressure value can be obtained between the difference between two unique oscillation pounds. So this sensor has excellent characteristics which required for accurate measurement, such as stability, reproducibility, sensitivity, and the temperature characteristics. So this slide shows the relationship with NMIs with the different countries. And since 1997, we responded to the individual requirement from NMIs, especially for small size pressure transfer standard. Okay, so this is we use for these sensors and the multi-manometer series are adopted as a transfer standard for CC level and also region level, like A, P, and N, A, M, APMP, for international comparisons. So there are two examples for transfer standard for international comparisons. One is the APMP, and the range is 1 pascal to 5K pascals differential. And the pilot LMI is the LMI Japan, the AISC. On the right-hand side is the CC level. Pilot LMI is the NIST. The two examples. So now I would like to talk about the improvement of sensor characteristics. So this is I'd like to show some activities collaborated with the NY Japan and AISC. So since 2016, we had some collaborative research with NMI Japan. So there are this purpose is the characteristics improvement and range expansions. So based on this improvement, we use for international comparisons as accurate as possible. Scheme is we prepare some sensor A and then move to the MIJ and then calibrate it by their highly advanced technology with the national standard. And then that's back to the Yokogawa and then calibrate it with another sensors, sensor B. And then sensor B back to the, go to the LMLIJ and then calibrate again and then to compare. So these cycles. So as a result, so left-hand side is a conventional RFG, calibrate adjusted by Yokogawa calibration system. And the right-hand side is improved sensors, calibrated by NMIJ calibration system. As you can see, so there are significant improvement. So these activities introduced at the APMF, Asian Pacific Measurement Forum in Niigata, Japan. And also this activity achievement is published in the ASTA IMECO. So as I mentioned, now we have many improvements. So these improvement sensor is using the latest manometers. We have various ranges. So, so basically, because of very much improved performance, maybe you have some older versions, but I recommend to replace because you try to keep your system as accurate as possible. Okay, so this is one of application we have Google digital manometers. This is the provision of standard of blood pressure monitors. So this activity is based on the Minamata Convention on mercury. So used to be, so this is a pressure, blood pressure monitors. And used to be the manometer using the mercury is using. But because of some Minamata Convention on mercury, to concern about the environment pollution and the risk to the health. So now we change in Japan that we already changed our solutions. So new digital standard. So advantage is eliminate the health risk due to mercury exposure and also automate inspection process. Okay, so this is the last slide. So there are some technical execution area. So we have a booth. So we have this 7300, CS700, 7300, and also 2558 as some of product. So I appreciate you if you stop by our booth to see our product. Okay. Thank you very much for your attention. Thank you. Thank you.
Thank you, Mr. Masayuki, for presenting about their products and their applications. Any questions, please? Thank you very much. I would like to request chairman of this session, please brief all the about my presentation in within 2 or 3 minutes.
First of all, I would like to thank all the speakers of the sessions. We had 4 wonderful sessions. There were some small glitches also, but for such an event, which is very huge, and we are having so many technical knowledge being shared, these glitches are nothing. And we had a first session by Professor Sain. So he talked about PM 2.5 and 10, then NLHC, VOC. Then we had a session by Dr. Singh, Vati Singh. He is from Fair Labs, and he talked about the temperature and humidity standards and the facilities available in Fair Labs. And we saw that they are having a very good facilities available. Then we had a talk by Professor Yang. He talked about the high pressure gas flow measurements. And last session was from Masayuki Okaji from Yokogawa India Limited. He talked about the instrumentation for pressure measurement, particularly he talked about the manometers, and also talked about the improvement in sensor characteristics. So I'm really thankful to all the speakers. Thank you so much for sharing your knowledge.
Thank you, Dr. Pavan Kumar Kankar and Dr. Nahar Singh for chairing the second technical session. Now I invite Dr. Pavan Kumar Kankar to felicitate Dr. Vati Singh with the token of gratitude. Dr. Vati Singh, please. I request Dr. Kankar to felicitate Mr. Masayuki Oka with the token of momentum. Thank you, sir. I further request Dr. Sanjay Yadav, sir, to felicitate Dr. Kankar with a token of remembrance. I request Sanjay Yadav, sir, to felicitate Dr. Nahar Singh with a memento. Thank you, sir. Now I invite you all for tea outside the auditorium.
Continue करना है session.
Tea break नहीं होगा।
जो जो जाएगा वो चाय पी लेगा और अब कंटिन्यू करो, हमारा सेशन खत्म नहीं होगा। आप वो करो,
कंटिन्यू करते
So I welcome you all for the technical session 3. This session will be chaired by Dr. Ranjana Mehrotra. She is the former chief scientist at CSIR National Physical Laboratory and has served as head quantum phenomena and applications division and physico-mechanical metrology division. She has published several research papers in SCI journals and completed several sponsored projects. Presently, she is chairperson of Lighting Related Committee of Bureau of Indian Standards, India.
Thank you, Komal.
Thank you for a nice introduction.
I can't.
Welcome.
Find it.
फोन करो ना और मैनेजमेंट है कहाँ आपके हाथ में यहाँ कोई भी नहीं है हाँ? सेशन में बैठे बड़ा गुस्सा आ रहा है सारे के सारे भाग जाते हैं
This particular session has four presentations. The first presentation is by Dr. Harish Kumar, and I can't find Dr. Harish Kumar here. So may I request Mr. G. Sundarvalia?
It is online.
Are you online, sir? Hello?
हाँ प्लीज प्लीज PPT है क्या यहाँ पे?
माइक की आवाज नहीं आ रही क्या माइक की आवाज अरे कौन से अब ये बढ़ाओ ना फेडर बढ़ा 3 नंबर हाँ बढ़ा बढ़ा यार मेरा सही चल रहा है और
ऑनलाइन दिख रहा है आपको?
नहीं है सुंदर left side.
Sir, are you ready for the presentation?
Yeah, now it is unmuted. Are you able to hear me?
Yes, sir, very much.
Okay, okay.
Sir, so are you ready for the presentation right now? Because the first speaker is not there right now. So we would like to request you to take the presentation. Okay, sir?
Yeah, I'm ready, but I have to share my PowerPoint.
Yeah, please share your PowerPoint, sir, and because we are running short of time, so I request you to do it within 15 minutes. Please, sir.
Wait a minute, please.
Camera
Because I thought there is a T session and mine will be second.
Yes, sir. Yes, sir.
Give me 1 or 2 minutes.
Sir, please, we wait for it.
Yes.
Please, your transparency, sir. Sir, please unmute yourself. Unmute yourself. बताइए कि शेयर कैसे करते हैं शेयर कैसे डिफिकल्टीज
नो
तो उन्होंने किया है ना हाँ
यस
अब अनम्यूट हुआ हाँ यही
Excuse me, madam, you give me 2 minutes because I thought there is a T section, then mine is second. Okay. I just want to share the PowerPoint, that's all.
Okay, sir. Please take your time.
Yes.
Excuse me, sir. The first person has already come. So, should we take him first if you permit? को फोन कर लेंगे प्लीज। वो तैयारी कर ले, हम तब तक दूसरे को दे देंगे। हम आ गए थे, अभी सब जरूर कर लेंगे। किसका काम है? किसका काम है? बाहर आदमी बैठे हैं।
अंदर है ये बेटा
Please unmute yourself.
Yeah. Is it okay, madam? Are you able to see my PowerPoint?
Yes, sir, we can see your point. So,
Okay, can I?
Yes, sir. Sir, let me speak about for you. Sir, Mr. G. Sundarvandir is the director in charge of Fluid Control Research Institute, FCRI, under Ministry of Heavy Industries, Government of India. Sir, please try to finish within 15 minutes, sir.
Okay, madam.
Please, sir.
So, respected chairperson, Dr. Ranjana Malhotra, co-chairperson, Dr. H.K. Singh, my co-speakers and other participants, good afternoon to all of you. Let me express my sincere thanks to the director of NPL, New Delhi, Professor Venugopal, and Dr. Sanjay Yadav, the conference chairman, then Dr. Shivkumar Jaiswal, the convener, and other staff members who are organizing this conference for inviting me to give a speech. So, okay, 15 minutes is given to me. Anyhow, I am going to constrain my speech to large water flow laboratory, which is a unique facility in India as well as I can say in the world, I can say, because if you go to websites, you cannot find any such facility. The FCRI. So the FCRI, Fluid Control Research Institute, has been the foundation stone laid in the year 1984. Then it was registered under Society Act in the year 1987, and it was dedicated to the nation by then President Honorable Sri Venkatraman in the year 1989. Our main activity is the third party certification for flow meters and control valves. Am I audible, participants or madam? Madam, am I audible? Hello?
Very well.
Am I audible?
Sir, we can listen you very well.
Okay, okay. So the main work is third party certification. So for that we require flow facilities, test laboratories. For understanding, I can divide in a broader way, that is liquid flow laboratories and gas flow laboratories. These are all the main two laboratories in FCRI. In liquid flow, we have water flow laboratories, oil flow laboratories, and exclusive facility for domestic water testing. Then gas flow laboratories, again we have air flow laboratories and gas flow laboratories, NG50 and CNG 250. Of course, we have supporting laboratories also, like physical standards lab, where we can keep the reference standards and get it calibrated and make it traceable to national and international standard. Other one is environmental quality laboratory, where we can do the calibration of noise and vibration. Shakers are there. You can calibrate accelerometers, hydrophones, etc. Then lastly, electrothermal laboratory, where we can calibrate the electrical parameters like voltage, current, and also thermal parameters. We have temperature baths, chambers, so thermometers, etc. We can calibrate RTDs. Now I am going to stick on to this water flow facility only. So coming to water flow laboratory, we have 600 mm water flow laboratory, 100 mm laboratory based on the size wise, and the largest one is 2000 mm laboratory. The 600, we started with the 600 mm water flow laboratory. The main fluid is now water. We have 4 pumps. Now we have 5 pumps of capacity, 3 pumps 3000 and 2 pumps are 500. So you can get around 3000 meter cube per hour with a pressure of 2.5 to 3 bar. Then with a pressure of 10 bar, you can get around 1000 cubic meter per hour. We have a concentrate tank also. Then reference flow meters are electromagnetic flow meters. Here we are using the basic primary method, gravimetric weighing method. That is the most accurate method for flow measurement, water flow measurement. See, if you look at this figure, these are all the pumps. Then it goes to the concentrate tank. Coming to the test section, there are various test lines available. These are all the reference flow meters. Then this upstream control valves, downstream control valves. It goes to the diverter. Diverter, there's a small one. These are all the weighing tank. One is 2-ton capacity, other one is 20-ton capacity. These are the diverter weighing system. We are using sphere control valves for downstream control. And so normally your flow meter will be fitted in this test line with the required upstream and downstream lens. Then depending on the requirement, you can select the various flow ranges depending on the Reynolds number range, and you can calibrate it. Depending on the accuracy requirement, either you can select reference flow meters, that is a secondary calibration, or you can go for a primary calibration. With the primary calibration, this weighing system, you can achieve an accuracy of better than 0.1%. See, this gives you the table. For mass flow rate, you can get better than 0.04%. That is up to 250 tons per hour. For higher range, it is better than 0.1%. Then volume flow rate I have given here 0.4% to 0.25%. And the total volume, it is again 0.05%. This gives the capability and accuracy levels of that water flow laboratory. This is up to 600 mm. These are all a few photographs of our 600 mm water flow laboratory. These are all the test lines. And this is the sphere valve. See, this is upstream. This is the flow direction. It goes through the bend. A vertical pipeline will be required to ensure the conduit is running full. Then there is a diverter system. This is small diverter. This is a big diverter. Then it goes to the weighing tank. Okay. So for measurement of flow rate, you can just start diverting. A timer will parallelly start. So everything is automatic. It will collect water for a particular time. Then automatically it will go back. The timer will tell you what is the time, so you can find out the mass flow rate. So this is a little better view of diverter system. This is a big diverter. This is a 20-ton weighing tank diverter system. This is a smaller 2-ton weighing tank and diverter system. At the bottom of the weighing tanks, we have fitted the load cells. This is another view of the existing water flow lab. These are all various test sections. This is the biggest one. You can go up to 24-inch and 12-inch, 8-inch, and less than that. Okay, this is upstream and this is downstream. See, in this water flow lab, after a few years, we were receiving many quotations for calibrating small flow meters, even NAL, HAL, ISRO, some 15 mm turbine flow meter like that, Then using this big lab for that is very uneconomical. So later on, we have developed another lab called 100 mm water flow lab. So whatever the flow meters or walls coming 100 mm or less, we will shift to this lab. And accuracy, everything is same, comparable to the earlier one. Now the question is, There are requirements which is higher than 600 mm diameter. So how you are going to take up? One is indirect methods. One is scale down model study. If 1000 mm flow meter is coming, I have only 600 mm line size. So I may have to go for a model. Then I have to calibrate it, and I have to finalize a non-dimensional parameter. The non-dimensional coefficient I have to apply to the higher size also. There are uncertainties in that. Or you can go for a bypass technique, that is also not so accurate. Then insertion flow meters also another possible way. See, if you look at this figure, these photographs, this is the water supply pipeline in Pune. 3000 mm diameter is the pipe. So we wanted to calibrate the electromagnetic flow meter fitted in this pipeline. So our people went there with 1 meter length the insertion flow meter. We have inserted this way, then the opposite side, then vertical, like that, or the way diametrically opposite places we have to take the velocity survey. Then we have to average it. But by the time, flow rate may not be constant. Flow rate, at a time we have to take readings for accurate measurement. But practically this is only possible. You have to insert here, then go there, run to the opposite side and do this insertion. Like that, this is also causing inaccuracy. So this is another similar example. This is a 1600 mm pipe. I went to APGPCL Rajamundri. There also big pipe is there. Then smaller anubar we have calibrated in water flow lab. Then assuming the coefficient is constant, we have put it here. This is again the APGPCL. So direct methods. Okay, insertion flow meters, that is also not good. Then calibrating, see existing pipeline is 600. What you can do if you are having 1000 mm for calibration, with using expander you have to fit it. But if you are doing like that, you are not changing the flow rate because your flow rate is limited, but you are increasing the pipe diameter. So naturally the velocity will be less. See, for example, you are having only 5000 cubic meter in your lab capacity. So you are having 600 mm pipeline. You will get 4.9 meter per second. But if you are increasing the line size for the same flow rate, what will happen? The velocity will be coming down. Okay, if you are going for 1000, say for example, the velocity will be still less. If it is 2000, it is less than 1 meter per second. So you will have to compromise on velocity. See, if you look at the error curve in flow meters, this is for electromagnetic flow meter, the accuracy or error will be constant after a velocity of 1 meter per second. So less than 1 meter per second, the error is not constant. So normally, if you are using a smaller size lab for calibrating higher size flow products, you are calibrating in a inaccuracy level. So keeping all those things in mind, the indirect methods are not so good. So we have made a facility in India, that is in FCRA, which can cater up to a line size of say 2000 mm diameter. So this is the large water flow laboratory. 5 pumps are there. The total capacity, the main line size is not 2000 mm. The total capacity is 15,000 meter cube per hour. Okay, so the flow rate we have increased 3 times of that of the existing water flow laboratory. Similarly, line size also we have increased. So these are specifications. This is the existing, the large water flow laboratory. This is established in the year 2012. See, this is actually 1200 mm pipeline. This is designed up to 2000 mm, but recently we have calibrated flow meters of PowerPoint. Okay. So higher sizes also we have done for 2700 mm dia. electromagnetic flow meter with using expander and reducer we have calibrated in India, that is in FCRI. Similarly, 3000 mm, for that 2000 mm is for adapt Pune, and for Krone, very many 3000 mm diameter flow meters we are calibrating in water flow lab, large water flow lab. See, this is 900 mm electromagnetic flow meter. This is now 1200 mm electromagnetic, this venturi meter. This is 1600 mm venturi meter. See, micro precision. This is a 1600 mm venturi flow meter. You cannot calibrate anywhere in India. So now we have this facility, large water flow facility. So this is another view of 1600 mm venturi meter. This is 2700 mm electromagnetic flow meters we have done for Adapt Pune. See the calibration curve. Of course, I can admit one thing. This is 2700, so the velocity also not 1 meter per second. In this 2700, the velocity is 0.7 meter per 79 meter per second. I have no other option. Okay. Then this is 3000 mm flow meter for Krone. That assembly, everything will be 2 cranes we are using for assembling. This is another view of 3000 mm electromagnetic flow meter. 3000, not 300, sorry. This is a calibration curve for 3000 mm sorry, electromagnetic flow meter. They have asked to calibrate at a specific point, so 2 points we have taken. The results are very good. Again, the velocity is 0.5 meter per second. Okay. So with this, what I would like to say is, now we have established a very large water flow laboratory in India, that is in FCRI. So customers started coming here. So we need not depending on the indirect methods. So directly we can use it and we can get a better results. Okay. Thank you very much.
Thank you, sir. Thank you, sir. That's something very strong. Is there any question? I think we can take one question, either from the audience or anyone online. Any question, please? Since there's no question, I will give let's thank sir for a wonderful talk. Thank you, sir. Thank you so much.
Thank you, madam.
So the next talk in this series is Dr. Harish Kumar. Dr. Harish is Assistant Professor at Department of Mechanical Engineering, National Institute of Technology, Delhi. Dr. Harish was also working in CSIR NPL as a scientist. He did his PhD from CCSIP University. He is also life member of Metrology Society of India. Dr. Harish is a very dynamic young man and doing a lot of research work in collaboration with NPL as well. So I request Dr. Harish to give his presentation. Dr. Harish, may I request you to take only 15 minutes? Okay, thank you.
Excuse me, can the facilitator switch on the audio? Virtually, we can't hear anything. Thank you.
अरे क्या है आप ये जो कराते हो अभी अगली बार आपने अनम्यूट करवाया वो ऑनलाइन ज्यादा बहस नहीं करते ठीक है ये ऑफलाइन हो रही है हो गया सर हाँ चेक करिए हो गया चेक मतलब ज्यादा नहीं बनते सर बोलिए बोलिए
Anyone online, will you please let me know if you can
Yes,
hear?
we can hear you now. Thank you. We can hear.
Thank you. Sorry from our side, sir.
So this talk is basically intended to investigate two different areas: additive manufacturing and metrology. Additive manufacturing, as we know, we are basically having a manufacturing technology which is having addition. So we're not removing like conventional manufacturing. So additive manufacturing and 3D printing, generally both are taken together. So we would like to correlate it with metrology. So whenever a new technology comes, a realistic assessment is must for its adoption on wider level. So this talk is basically aimed to highlight challenges for additive manufacturing methodology. So very new area, and up to best of my knowledge, National Physical Laboratory should also think in this area. So I'm basically trying to provide a glimpse of this area. So this talk includes introduction, additive manufacturing, classification of additive manufacturing, role of additive manufacturing industry, concept of metrology, advanced measurement methods, challenges, future scope and reference. So manufacturing. So in brief, in a nutshell, what I would like to say, manufacturing can be basically three types. Conventional, whatever we are doing in our workshop, subtractive manufacturing. Another is non-conventional manufacturing, which we generally call micro machining, like EDM, ECM, etc. such kind of thing. And another is advanced manufacturing, in which we basically cover digital manufacturing or additive manufacturing. So the main intent of all the three processes is same. They have to produce a desired component, but the methodology is different. In first two, you are removing the material. In first, material, more material to be removed. In non-conventional, basically micro material to be removed at micro level, micro machining, and in advanced manufacturing or digital manufacturing or additive manufacturing, you use whatever through the tongue. So you are basically going to do the manufacturing of the desired component without any metal removal. Practically no metal removal. I will also come to discuss, yes, there is also some material removal. So additive manufacturing, as this main talk is here. So in additive manufacturing, we are basically adding layer by layer. So for example, if I have to prepare a cube of 1 mm by 1 mm by 1, for example, if you want to prepare it with conventional techniques, so what you will do? For example, if you are not having available 1 millimeter by 1 millimeter by 1 millimeter, so what you will do? You will take available size of the specimen raw material available to you. You will machine it to the desired shape, desired dimensions. But in additive manufacturing, you are not doing so. You are basically fabricating this by layer, So for example, your first layer 0.1 mm, then 0.1 mm, then 0.1 mm, then 0.1 mm, then 0.1 mm. So this is the way you are fabricating through addition by layers. So what is the importance of additive manufacturing? Generally, what we have the tendency, we are looking only for one side of the technology. Whenever a new technology comes, we always are fascinated by it, and we generally focus only on its positive aspect. But what about the limitations? So additive manufacturing, of course, it is a newer technology in comparison to the existing technology. So it is cost effective, less workload, time saving, because it is digital. So whatever you are planning to do, you can imagine, you can make it design, drawing in a software, you can do slicing, and then you can fabricate through the help of printer. But what about its other aspect? So classification of AM process, basically your raw material can be liquid, powder, or solid based. According to liquid based, we can have steel lithography. In NPL, if I'm not wrong, we have been used STL for several decades. Jetting system, direct light processing. If we are using powder based, we can have selector laser sintering, 3-dimensional printing, fused metal deposit system, electron beam melting, selective laser melting, direct energy deposition, etc. These are some of the methodologies. And if you are having your solid raw material, then fused deposition modeling or fused filament fabrication, sheet stacking technologies, or fused filament fabrication. So these are some of the different techniques of additive manufacturing based on your raw material. Whether your raw material is liquid, whether your raw material is powder, or whether your raw material is solid. So how this additive manufacturing has been able to garner attention in industrial applications. So if we see, for example, its main application, if I must say, it is in the aerospace industry and the medical industry. For example, if I would like to discuss a very common case study which was a headlines about 7-8 years back, Johnson & Johnson, a major giant in medical implants, was facing about 10,000 suits in federal court, USA, for its faulty hip implants, because those hip implants were available of standard size. And these implants cannot be accommodated by body of each and everyone. So their even size difference on micro level may create a lot of problem to your body after replacement. So what was happening there? People were facing problems post operation once their implants were done. So there were about 10,000 suits filed against Johnson & Johnson, and they declared themselves bankrupt. So now the question comes, why we are discussing that case study here? Because whenever you are using these standard sizes, a limited customization is possible. And additive manufacturing is having main advantage of the customization, because you are not using it for mass production. People are working for mass customization kind of technologies for 3D printing, additive manufacturing. But as of now, they have not been implemented on ground so far. So basically, additive manufacturing as on date, even I am also using it only for prototype study. So customization is possible. So that is the reason you will see now most of the implants, even if you're going to a dentist, it generally asks you now, if you're going to go to dentist, whether you want 3D printed or conventional. So these days, these implants have been fabricated with the help of 3D printing technology, because with the help of CT scan images, we can generate a 3D model of whatever the implants or whatever the part you require. And very precisely, you can fabricate the same depending upon the material, which may not be chemically affecting your body. So, and the next case is aerospace. The government of India is very much focusing over Make in India, Make in India. Your plane, for example, if I'm talking, some of the planes are being assembled and their parts are fabricated and manufactured in the country. But what about those planes who were supplied by Russia in 1960, 1970? Even their drawings cannot be digitized as on date. Even the OEM has stopped producing such parts. But those planes are running in the sky, flying. If any component fails, what you will do? So HCL has been working on very large scale of producing those very small but critical parts with the help of 3D printing. So if you will check on the Google, BMW has started some development of some prototype of cars fabricated with the help of 3D printing or editing and printing. So why? Because this technology is new and its maturity can be ascertained only after a long and realistic evaluation. So that is the reason AI has garnered a lot of attention in various industrial applications in especially past 1 decade. So even if you will see, even in the schools, there are small printers, DIY kits. Kids are doing, they're trying to learn. So these are some of the applications like skull implants, biomedical implants, some aerospace parts, automotive parts, etc. So this is just some images taken from internet. So now I would like to ask you, you have to prepare some column and you want to keep it hollow and it is closed from top and bottom. Is it possible with the conventional manufacturing technology? Of course not. How you can remove the mass from inside without piercing it? But in 3D printing, because you are fabricating layer by layer, so whatever you can model in your software within the limitation of the printer, you can fabricate it. So you can see some of the designs like topologically optimized hinge for aerospace industry, 3D printed injector heads, 3D printed RF filters for communication satellites, and 3D printed rockets. These are some of the case studies which we have taken here. So what is the main intention? That this technology is, of course, now we are using here. But what about its metrological assessment? Whether the specimen printed by 3D printing, for example, 1 millimeter by 1 millimeter by 1 millimeter, is really 1 millimeter by 1 millimeter by 1 millimeter, or it is 0.99 something plus minus. So that metrological assessment of 3D printing is yet to be done on very large scale. Up to best of my knowledge, NIST USA and University of Nottingham, they have been working on this area on a very large scale. So now, how you should apply metrology in 3D printing? How? Basically, whatever you have done in 3D printing, whatever technology you are taking, no real-time metrological assessment is possible. Like, for example, if we want to check in print that how much layer thickness is there, each layer thickness, that is not possible. So what we are doing as of now, we are basically using 3D scanner, and with the help of 3D scanner, we are preparing its CAD design again, and we are doing its 3D slicing, then 3D printing, post-processing, 3D. So how it is doing? So first reverse engineering and another is new idea or concept. So if you have already prepared a component and you want to check whether it is having to fulfill the decided dimensions or not, then what you will do, you can use the 3D scanning. And with the help of 3D scanning, you will be able to prepare CAD design. And then you can compare the dimensions of the developed one and whatever you got from the 3D scanning. But now there is one problem. What is the uncertainty of measurement of the 3D scan? Very big question. If you ask any manufacturer of 3D scanner and you ask him, you give me uncertainty of your 3D scanner, He will say no. So whenever there is no comparison, then can we really ascertain the metrological capabilities? No. So that is the main challenge of in front of additive manufacturing, to sustain it as a practical and viable solution or alternate to the conventional manufacturing techniques. So what we should do, this part we have taken from our one of the very recent review article. So we have to do either inline metrology, online metrology, at-line metrology, or offline metrology. So offline metrology basically once product is prepared. Inline, whenever it is being prepared. Online, during the whole process. So in inline, there is no feedback. In online, there is feedback. So for example, your layer thickness is 0.1 mm. Whether 0.1 mm layer thickness was in previous layer or not, it can be ascertained here. So whatever the various quality control and inspection for methods for 3D printed parts, so basically dimensional inspection, external surface inspection, internal surface inspection, or specific surface roughness test. So if you go for dimensional inspection, you can use CMM, gauges, and light scanners. If you're looking for external surface inspection, you can go for visual, which is not recommended at all, penetrator E-magnetic method. And if you're looking for internal surface inspection, then you can look for different techniques like ultrasonic radiography or tomography. So if you're looking for specific SR testing, then you can use, you can have setups for surface roughness, etc. So these are certain common measuring and inspection methods, and on the basis of certain data from some research article and websites, a rank has been given to these methods. So you will see that visual and naked eyes, direct comparison, laser tracker, tactile CMM, optical CMM, computer tomography, interferometry, optical surface topography, pyrometer, etc. So what is the main intention? How you should apply these techniques and whether these techniques are really able to help you in metrological assessment of 3D printed parts. So in additive manufacturing, basically you have materials very important, additive manufacturing setup, modeling and simulation, qualification and certification. So this is not a conventional technology. You need a highly skilled workforce and you need highly specialized setup. And what is the major drawback of additive manufacturing? Your most of the material are still proprietary. So if very few printers are available, especially in metal printing case, which are using open source material. So these are certain major important challenges in terms of additive manufacturing. So if you would like to assess the AM part quality issues, so first important, very complex part shape, because additive manufacturing you are using only where you cannot prepare your that specimen with a conventional techniques, because conventional techniques have already much matured. If you can prepare your part with a conventional technique, then why you need to purchase a 3D printer of 10 crore? Your workshop is already there. Workshop is already there with me. So if my specimen can be prepared on simple lathe, simple milling or CNC machine, then why I should look for some 3D printing setup? So voids and entrapped particles. In 3D printing, generally we are heating our raw material, whether liquid, whether powder, or whether solid. So the main issue is void and entrapped particles. The particles may not be completely melt. Internal geometrics and undercuts. This is a major problem with the 3D printed parts and high surface roughness. So post-processing is generally required for 3D printing part. That's why I used initially in the presentation that even additive manufacturing requires some of the machining or finishing process. So you can see if you are having such kind of complex shape, then is it really easy for us to ascertain their geometrical features? No. So yes. So these are some of the issues with additive manufactured parts. So similarly, you can see such kind of shapes are there. Then metrological assessment is really very difficult. So you can see the typical same images. Your material is not completely melt. So you can see solid part are there. These granules. So what should be the next course of action for metrological assessment of 3D print? So basically the fundamental research will be required to create the next generation of dimension, texture, mechanical and chemical measurements of additively built components. Because whatever the shapes we discussed, they cannot be, their dimensions, for example, we cannot measure on our conventional CMM. So how? The limitations of the current equipment, requirements for the necessary precision and measurement need speed for AM operations will be overcome by new methods to instrument design that draw a combination of knowledge and invention. To make AM components of consistently high quality, producers will understand and optimize the properties of their metal powders, polymer powders and other materials such as ceramic and polymer. So until and unless we are able to overcome such issues, then we cannot really ascertain AM for our practically viable solution for our most of the engineering or scientific applications. So I'm thankful to my collaborator, Dr. Girija, here, as well as my research scholar, Mina, because they have substantially contributed to this work. And these are some of the references.
Is there any question? I think we can take one question. Any question from the online audience?
No question.
No in chat box?
No.
Thank you, Dr. Harish. Thank you very much for a very nice talk. Thank you. So the next talk in this series is by Dr. R.K. Kotnala. It is my pleasure to introduce Dr. Kotnala. Although he's a well-known person, he doesn't need any introduction. But Dr. Kotnala is the chairman of National Accreditation Board of Testing and Calibration Laboratories, NABL. Dr. Kotnala did his PhD from IIT Delhi. He has been hailed as an innovative inventor in the field of silicon solar cells. Dr. Kotnala was our colleague in National Physical Laboratory. He was chief scientist at CSR NPL. He is also Rajaraman Fellow of Department of Atomic Energy. He has made good contribution to the hydroelectric cells, environmental sciences, humidity sensor, spintonics, solar cells, and many other fields. There are a number of publications he has to his credit in SCI journals, and there are many more. Actually, his biodata is too long. If I keep on reading, I think his talk will be in a lesser time than his biodata is. So I request Dr. Kotnala to start his talk. Dr. Kotnala, please.
Thank you, Dr. Ranjana, chairperson for this session. I'm thankful to Metrology Society of India and as well as Director NPS that I am with you. My some of the senior colleagues are over here. One of them is Dr. Dixit and Dr. Sanjay and others. This interesting topic, which is if one reads it, challenges and issues for the 21st century in Indian context to quality standards accreditation. A solution for problems or a fresh problem. The title itself speaks of some there be challenges and issues for the coming years, what is happening, and quality standard accreditation. Why I have chosen this topic? Because I understand both the sides. So before getting into the other side, that is what exactly I want to speak, that whenever we are going for any kind of accreditation is a solution for problems or a new problem appears over there, which you have to tackle, struggle to get ahead. So a glimpse, I'll say the easy glimpse is given, and you will find things to be different. Of course, Dr. Ranjana has already spoken about myself, why I wanted to show this one, that I have been with the ISO 17025 in the year of 1996. So I have done that course. And not only on this, I am involved in the gold, coal, water, BNBs, Bharatiya Nirdesh Dravya, which are said to be the reference material. And not only on this, when we talk about the different standard reference standards, and also work for metrology 22 years in NPL for magnetic primary standards, besides my research work, because this I was taking up with a very small time initially, and most of them were with my research work, but the both I could do. And why this background I have written that we work for metrology 22 years in NPL for medical standard, because now I have seen both the side. As you know that I'm looking after the NABL also. And in NABL for the last 2 years, what kind of problems are there, what industries are facing, what labs are facing, and what accreditation body itself means NABL is facing. So that I want to talk about so that we can think in a different form. It is a very important for industries, labs, and for the public in general. So public in general, because we are talking about the quality system for the public. In case of a magnetic measurement for the society, when I did it, that was a 10 magnetic measurements up to I brought it up to the BIPM level, and project coordinator for the super technical building conceptual design to build works related to the 7 SI base units in a newly created metrology building at NPL. Based on ISO 7025, area 12,500 square meter, super technical building, 5th in the world. Because here NPL has housed all the base units and the drive units setup. This was done in 2014 finally. In the 4 years I could coordinate the whole work. Magnetic measurements is one of the strategic parameters in most of the industries for motor, rotor, transformer, machines, dynamos, etc. So this realization was done in the previous century when I was doing this work. Started. Special efforts were to formulate technical solutions for LED meters to prevent them from tampering of external AC and DC magnetic field. So whatever was the international standards for stray magnetic field, which was affecting the energy meters inside any industry or any other place, even I can say that the workshop. So the digital meters were having the problem for the stray magnetic field, but the international standards were at a very low values. And here we are doing tampering with the higher values of the magnetic field, which was being generated. So the new specification was set up, which is done with the Central Board of Irrigation and Power in Chanakyapuri. So I did for 2 years the work on it. I provided the consultancy with my team on this very important, and crores of the rupees were saved during even 1999 by implementing the new. So for society, what we are doing, what is the role of our metrology? Because we are doing in the National Physical Laboratory, so we have got this. This was the primary standard. I will not talk about this. Only I'll just rush through my slides. The nuclear magnetic resonance is the basis for our magnetic field, because any of the primary standard should be now based on the either a sum of our fundamental constant, here is the gamma, frequency directly proportional to the magnetic field. So the NMR resonance is being carried out to measure the magnetic field. So that is why it is called the primary standard for the magnetic one. So I'll not talk about what kind of homogeneity I need, because my purpose is different on this. So this is the way what we normally need: national standard, transfer standards, precision instruments, how the chain is formed, and everyone is important, because precision instruments is for the industry, for the labs, and transfer standards is provided by the NMI and then to the regional agencies. In case of the magnetic standard, when it was to be started, so one can see that what kind of inputs are needed, and then we come to industrial and social benefits. R&D on magnetic materials also I initiated within the 3 years after establishing this lab in 1998. So national standards, and definitely that time at the initial stage, PTV lab support was needed, because it was a completely new topic, new parameter for India. But it does not complete, because if we get something from the PTV lab, means again I'll say the foreign collaboration, we have to go for development of new measuring methods, because if we don't do, the job is incomplete. We will be doing measurements only what has been done by the others. So we have to look at our industries, what they need, and if there are some of the R&D labs also needs some standardization. So for that, new measuring methods are to be developed. So here one can see that how the primary standards, then magnetic field as sensors, means Hall sensors, soft magnetic materials, because we produce millions of tons for the export and as well as for our use, the flux meter calibration, and ultimately it comes to industrial metrology, where Gauss meter calibration percentage is given for the accuracy. Extreme flame method, electrical field power loss, it is one of the most important for any rotating machine, whether it is a motor, pump, generator. Then the magnetic flux from the search file. So this all work was done, carried out. It appears simple in the slides, but when we come to our measurement, you can see the three-dimensional Helmholtz coil, where we have to go for the magnetic measurement at the level of the highest level of uncertainty, because the first, these three, they are not only shielding the stray magnetic field, but also Earth's magnetic field, 3 axes. So in the lab, one can see that what we do, and it is an NMR Gauss meter, how it is working. I'll not talk about it. And in this one can see also that what kind of measurements have been carried out. So beside that, because that was a smaller one, the bigger version is this one, which was constructed at National Physical Laboratory. And here we wanted that like a 400 Gauss or the lower values, which cannot be measured from the NMR Gauss meter. So that was developed. And then one can see the uncertainty is calculated for the field measurement. So how it is done, it's a really difficult, that is a central part of it where we generate the magnetic field. But these are the three axis, rectangular, rather it's a square, Helmholtz coil. Now looking at this, what we have done in that, so the specialized application test and calibration which are developed in magnetic standard for the industry. I'll just read them: precision, weight, susceptibility, magnetism task, Earth's magnetic field. So this is a precision weight when we talk. So here Dr. Dixit is sitting from the legal metrology. He knows very well that this was needed at the just turn of the century, 2000. And so that work I was doing that time for this light weights at the level of E1, E2, E5, this way. When then we come to the energy meter, must pass through magnetic field test, because without this magnetic field test, we cannot go for, it's a energy which is the main parameter to be measured, voltage, current, and power. But this is the needed, so we developed for this also. Conducting polymer included magnetic material as a EMI sheet, how it will work, MCV and pilot compass, how to calibrate it, because this was being done in this lab itself. Magnetic crack detector, NDT on ferrous parts, how to do it. So how the calibration is to be done. Then one can see paint thickness iron sheet, which is known as alcometer. It came as a boom because since we got the new paint techniques and the thin sheets of the car, again way back in 1985, so alcometer is being used in that. So that was also to be calibrated. Then MPFI, it's a multiple point fuel injection now. One, it is based on the solenoid, magnetic solenoid, how the petrol is to be, or the diesel is to be injected inside the carburetor or the pistons, how it can be done. So that is the MPFI, so that also. Then it is again aeroplane parts check for the residual magnetism, which is the magnetic indicator. It was being calibrated abroad, but now it is being done here. We help the Air Force as well as the HAL, then the other industries also. Then the power loss measurement for the transformer core and for any other. So these all test methods were developed in the lab. These are the few, there are the others also. So it is a direct service to the industry. I have shown that how the magnetic field indicator was developed with the help of our magnetic field, how it is being generated, how it is being measured inside our helmet squad. So that was a new for us. Same is for the MPFI, because fuel injector in automotives, how it can be done. So how the plunger will be taken, what will the material for it, how it can work for in a minute 1,000 times, off and on. So the material will go in different. So metrology saving power loss by testing electrical steel used as a core material in transformer. So that is another part for which one can see the steel frame measurement over here, this setup, how it works. It is given here. The power loss measurement in NPL and PTB are within the stated uncertainty between the 0.2% to 2%. One can see that how we have measured their power loss, very static power loss, and then our flux, then the PTB values are here, NPL values are here. So because that comparison was needed, because that's another NMI from a developed nation. So how do we calculate for this? I'll not get into it. The PTB lab, a single sample from PTB, a sling frame, and then our electrical, the steel strand sample, and then artifact. What we do as a national standard and then transfer standard means for the industries. Same is the situation for the transformer core, because the transformers are burning because of our quality of the core. For the core, I'll say on which the winding is done. So that is to be taken care. So that work was also done. I'll not get into the detail of this, but I'll just talk about the detrimental effects in efficiency and health of transformer by using recycled electrical steel. So this also I worked with the Power Ministry way back in 2014, that how we can really stop this recycled electrical steel, which was being used in the transformers and then sold in India, by increasing the custom duty on them, which was ever. So one can see that how much even the 0.5% distribution transformer efficiency, if it is increased, then resulting to the 4 to 5 billion kilowatt hour together. This is the specialty of it, but we think that the transformer is working, whatever be its efficiency, we do not talk of it. This is again indigenous setup. where we have melting influence test setup on energy meters. We are working on this. We are testing all the magnetic field, basic magnetic field for this. One can see the here setup customized power supply was created from the industry. So I was also using a vibrating sample magnetometer for my research and as well for the industry. So that was also calibrated. I'll not get into that what kind of parameters we did it with basically standardized, and that is why till today, even if I have published the papers more than 400 only on magnetic materials, not even a single measurement has been challenged by now. So uncertainty calculation is normally done. So that is again not a point. But this definitely global quality standardization for sustainable growth of economy and lifestyle of the country, we definitely need our accreditation because quality system is to be taken care. So food items, we have the healthcare items, defense items, war. For the war means the all war for the war, whatever we are equipment using, aeroplane we are using, agriculture, then clothing. So what is left out? Nothing. Electrical, electronic equipment. So all these are to be taken up. Infrastructure, civil, mechanical engineering, and others also. So when we talk about sustainable growth of economy, then the standardization of advantages for quality in production and testing, save resources, the most important part, fearless exports, boost confidence, and flawless production. So these are the four major, I'll say, the points by which we can really talk about the standardization and quality, because that makes things very different. Country's economy, when we talk about poor quality product, most of the developed nations are following that. And in our case, one can see that international quality standards, ISO, IEC, why we want conformity, all know very well. For the ISO, we are basically following the ISO series. For military standards again, because here we are working hard to maintain it, which includes even the tailoring information, environmental stress data, and the working test method. So there is an endless application which we normally say that we need to know. Then we come to a level international organization for accreditation, which we were knowing sitting in NPL, but my direct hands-on experience with this, and you should be, whatever I say, you'll be surprised or what. I'm the first chairman who has got a direct hands-on experience on the standards, directly and quality for a very long time. The other chairman had the very little experience on that. So in NAVL, you know very well, Chairman working. So it has become very easy for me to connect these two things. Because when you do the work on this, and we know very well that what is the ILAC, right? What is the International Accreditation Forum, IF, and FLAC, then these are the different bodies, agencies for which we think. And for the ILAC, we know very well it's not possible to have an accreditation body unless you have got a MRA. So ILAC has got it, MRA like this for the European Corporation, ECF, the Inter-American Accreditation Corporation, because these are the basic requirements. When we say that the accreditation body is to be formed, and one can see that 80 accreditations bodies recognized by International Accreditation Forum, by IF only by IF, in which from the NABL, it comes to be a NAFBC. So you can imagine, and the rest of them from the different countries. But NABL comes in a APAC, it's a different, the MRA is different there. So accreditation process in India, when we talk, the NABL has got the National Physical Laboratory, NPL, Bureau of Indian Standard, GIS, and NABL are three pillars of quality infrastructure. We all know. But the most important is assessor, labs, and industries are the key stakeholders as holdings and interconnectors of these pillars. They are the holdings and interconnect. Because whatever is happening, when we talk about the quality infrastructure at a ground level for the people, then the role is also very important for them. Over the past 40 years, the number of upgrade labs have increased exponentially, especially after 2012. Almost in every field, calibration testing as per this 17025, for the medical testing 15189, 17043, for the producer 17034, we all are following the assessing lab. This is the 8,000 caps are accredited by now from the NABL. The results produced by the red caps are acceptable among the member countries as NABL has mutual recognition arrangement stars. Because whichever be the country, they will just accept that what has been done from them. But the another part, which is the most important, that talks about challenge accreditation for a robust global quality system. What it is talking about, there are many issues which need to be taken care for the evaluation and for the development of accreditation services in India. The accreditation process needs to be redefined in terms of timing of assessment. Because the industry knows, because here some of the people who are from the industry, they know it. Even the NPL people know very well. There's this. The accreditation body staff must be competent and have knowledge about the particular type testing, calibration, and medical testing, etc. So that during the accreditation process, chances of wrong decision may be minimized. Because these are our basically challenges. When accreditation decisions are logical, then the number of appeals decrease. Because appeals are when there is a dispute that the lab says that the no accreditation has not been done and those parameters are not there. Conflict of interest is one of the most important. And impartiality should be taken care during the decision-making person. Accreditation body responsible for the right decision of accreditation. Because these are the very, very critical issues. Timing of new accreditation and renewal of accreditation is one of the burning issues these days. And it needs improvement to satisfy the caps. Caps means the laboratory which are lab or industry which is being accredited. So those are all the caps. It seems one accreditation body is not enough to cater the need of Indian industries, public labs in lakhs, because there are 3 lakhs labs which are doing the testing, calibration, and even the medical equipment. And NABL is able to do today 8,000. Even having a long, I'll say the long journey, that means one accreditation body is not enough. So we must have, because India has got a large population, everything is a big in size. So there is a need for other accreditation bodies as well. Of course, there are already efforts, and some of the foreign accreditation bodies are already sitting in India and they're taking business. They are considering that to be a business, not as the quality infrastructure for India, because we are concerned for quality infrastructure which is to be created. So standard for NABL and labs, NABL operates accreditation program in accordance with the requirements of the bill. Because this accreditation body 17011 from our APAC, ILAC, they are following this. The labs are accredited as per the quality standards. These are the standards which are being followed. NPL people know very well, and industries also know. What it talks about, NABL, MRA with ILAC and APAC, what we need, effective and speedy implementation. That's what is needed. Industry quality enhancement, innovation in standards, and quality infrastructure. That's most important to develop it. All these should be input, international industrial competence with quality assurance, and industry and testing lab interaction, hands-on training. So of course, some few of the things are being meant, means basically the input is going on and it's being taken care. for a robust global quality infrastructure, salient points to ponder. This is for all. That the what points we have to think of. Too much time taken by the accreditation body to accredit the laboratory and due to be too much time taken. To avoid the delay, the accreditation body should have adequate resources in terms of assessors for all the fields of testing, calibration, and medical. In fact, here I would like to clarify for any accreditation body, whether it's a foreign or Indian or assessors are the basically distinguished specialists and experts because they are measuring the basic parameters and giving their expertise which they have developed in the 20 years, 30 years of experience. So their role is very, very important for all the fields of it. Then to avoid the delay in accreditation should have multi-skilled assessors. For example, the laboratory has applied for pressure and mass index for this laboratory. The AB sends at least 2 assessors, one for pressure and one for mass. So these are the some of the basic things, but definitely to cut down the cost of laboratory, the accreditation body should send only one assessor who has expertise in pressure and mass. And we know very well that this example is given because pressure mass are very much correlated. They are very much based on that. And when we come to the other points, the repetition or demonstration of testing and calibration also takes time and money of the laboratory. Means we have to think in that terms also that how we can avoid repetition, we can save time and money both. Currently, the time taken by the accrediting body to accredit or renewal of accreditation of the laboratory is very long. It can be cut short with a proper way. The fee for accreditation is very high from our economic point of view for the small labs. It is to be noted that the accrediting body is no profit, no loss organization at least in India. Therefore, the accrediting body need to rethink about the fee of accreditation. So what we have to look at that finally it should be competitive for any of the accreditation body, and we have to look into because voluntary in nature, because our process of the accreditation body is voluntary in nature. So the fee is not for doing the business with the laboratories of this. So those points are really serious where we have to think and we have to consider in different way. Thank you.
Thank you, Dr. Krishna. Is there any question? Yeah, please.
Economical growth. And when we go for the social growth or economical growth, so we are limited only to the laboratory resources or particular industry organizations, laboratories, and limited to the income. So we are not are capable or we are not in position to cope up the social growth. Like I can give you example that the quality of the water in society, whether it is the safe water, bottled water, we have made the standards for the water, but we could not make all the drinking water which is supplied to the common citizens. That it is a standard. So like that, we could not do processing of certification. So there we are lacking the social development. And similarly, you will find that the same thing is happening in the industrial development.
Right.
We are able to do the very precision measurement and certification. But where the industrial growth is, for that requirement is the R&D. So we are not able to focus that our youth will go towards that side. Unless our youth are focused towards the R&D side here, our industrial growth will not go up to that industrial or whatever our, because the where the R&Ds is going on at when we are comparing Germany, Japan, USA, Argentina, France, and other places. So there a lot of investments are there in those very fields. And we are not in position that motivating the student so that they can go towards the R&D side and they can do the better research and can do the without the scientific research. I do not find that there will be industry.
I know you are right on this point with the industry growth and the social growth, and like a water for the drinkable water, you have said the government has given a lot of different schemes. And they are working, and the Quality Council of India, QCI, is also working on it to provide, to improve the quality of the well water in the different villages. So they keep on doing, and our role, because what I wanted to speak over here, these are the points where we want a quality infrastructure at the ground level. So for that matter, the accreditation body and our even NMI when we talk, where because from both the side I have been working. So it is definitely the duty of all of us, and also it lies on you also, because you have been with the consumers affairs ministry, where they take out some of the new legislation, the rules, and some support to the industries in the small labs. So that all is needed, and this has been already told in one of my board meeting, that why not to provide some grant to the small labs who wish to go for the quality standard. They should give, because they have enough money. So NABL, QCI has got a lot of money in their reserve. So that I have already spoken on it, and that will be doing it. But the only thing is that we have to push it. Thank you for your question.
Thank you, Dr. Putrana. There is one more question online, and the question is from Mr. Sarvamurthy. He says, "Dear Dr. Putrana, great contribution to NABL. Please elaborate the process of NABL accreditation." I think it is a very long question and long answer. Probably, I think Dr. Salamurthy can write to Dr. Kotnala, and Dr. Kotnala can respond.
I'll just
please.
Dr. Salamurthy, good evening, because we know each other very well.
Okay, okay.
Right. So what I'll do, I will give you a separate time that how accreditation is being done in the NABL. But because here I was just talking about the problems which are to be sorted out, the burning issues, challenges, and the role of our NMIs, BIS also, because which are our pillars, and the NMBL. And then the problem of the country. But how accreditation process is being done, that you can sit with me, you know very well, and I'll give you the time. And there is a Chakravarti also, Dr. Neeraj also, I will see all of them. We all can sit together, and I'll whatever the question will be there, I'll answer. Right?
Thank you, Dr. Kotnala. Thank you, Dr. Salamurthy.
Thank you very much for
Thank you, Dr.
even coming to the BC and looking at this. I'm really thankful. Thank you.
The next talk online. So the next talk in this series is Dr. George C. Thomas Watson. Is he online? Oh, we have the video. So let me
Workshop
introduce Dr. George C. Torres Jointman is currently working in mechanical metrology at Center National de Metrology, Mexico. He is working in force, torque, pressure, and vacuum metrology. He is also supervising hardness metrology and barometric metrology, where primary standards development and high. So please, a video. He has a video. He has sent a video. So you can see.
And your dear ones. Secondly, and also very important, I would like to thank the organization for inviting me to give this talk to you for this important 21st ADMET conference. I am sure that you will have not only new and interesting conference, but also you will enjoy it. It is my very most biggest regret I won't be there with you, but I will be in my heart. Thank you very much. I hope this conference is interesting for you. Okay, my presentation will be on the gap analysis of a pressure metrology laboratory. And I will talk about it by speaking firstly about a general introduction, then a general methodology, and then important issues to be considered in the methodology. I will then go to talk about the final analysis report, and we will end with the conclusions of this presentation. These quotes are very interesting. The first one, your problem is to bridge the gap which exists between where you are now and the goal you intend to reach. Also, when the gap between ideal and real becomes too wide, the system breaks down. So from here, we can see that gap analysis is important. We will go to introduction. The first thing to consider is that a gap analysis is really an assessment which provides a view of the difference between the current state of calibration and measurement capabilities, CMCs, compared to those required to achieve the desired level where we want to go. The analysis can also provide mainly three different things. One is a base to make the most of our capabilities. B, a set of objectives for corrections of deficiencies or for improvements. And C, a selection of calibration capabilities for possible accreditation. To do that, we have to look for 6 different things. The first one is the workforce. We have to make analysis of the workforce, also the technical documentation, the equipment, if we want more or better equipment, the environmental conditions of the laboratory, the quality management systems, and most importantly, the CMCs. If we want more CMCs, wider CMCs, or better CMCs. We will talk now about methodology. And the first part is to develop an evaluation. And to do the evaluation, the methodology start with the review of the current state of the pressure laboratory. Then we have to compile detailed information of the current capabilities and the CMCs of the laboratory. Then the technical parameters desired or a vision of capabilities to be achieved. Then the gap analysis. Using techniques such as the Ishikawa diagram and or the SWOT analysis. These two techniques are very commonly used, and we will talk about it later on in this presentation. Analysis of the necessary improvements for the measurements and calibrations to be achieved is the last part of this methodology. The process development of the evaluation methodology for the gap analysis of a pressure lab can be divided into different steps. The first step is to identify the area of analysis and to identify the current sources. That is, in the pressure calibration laboratory, which type of pressure we are going to measure and to calibrate. Differential pressure, absolute pressure, gauge pressure, negative pressure, or vacuum. The instruments to be calibrated, as you are very well aware, there are several types of instruments in pressure. Could be manometers, columns, dead weight balances, or other types of instruments. And then we have also to identify the standard references, the personnel involved in the laboratory, the procedures, and the laboratory area, the space that we have for the laboratory. The second point is to analyze the current state. And we can do that by doing an initial survey. This can be done with the local people, I mean the technicians or the boss of the laboratory, or even the administration would have all the information on how is running the laboratory at the moment. This detailed information can be drawn in the 5Ms methodology. We will also talk about this later on. To establish ideal future goals, that is, okay, we know where are we standing now. Now, what we want to achieve. We would like to have a recognized laboratory within the company, that is ISO 9000, or we want an accredited laboratory according to ISO 17025. The fourth step is to compare the current state with the desired goal. That is, first to evaluate general and technical requirements. Then we can use the techniques we just talked about, let's say the Ishikawa's diagram and the SWOT analysis. Step number 5 is to describe the gap and estimate the difference. In other words, is to summarize the recommendations to bridge the gap. And finally, to make a plan to close the gap. This is the most important thing. Otherwise, we haven't achieved anything with this gap analysis. We will look at the methodology details now. The first step is to identify the area to be analyzed and identify the current resources. That is the type of pressure. And as you may know, we have absolute pressure, atmospheric pressure, vacuum, and also we can measure gauge pressure, negative pressure. We can also measure differential pressure. So one pressure laboratory can do all those things or only one of those. The most common one is the gauge pressure. The second part in identifying the area to be analyzed and identifying the current sources is to classify the pressure gauges that we are going to use as standards and to be calibrated or measured. And there are many different pressure measurements. You certainly have seen this graph and these instruments for pressure classification. We have direct method and indirect method. And indirect method, you can use mechanical deformation, dead weight testers, liquid column, and indirect method is mainly used for vacuum. So we have ionization gauges, thermal conductivity gauges, and viscosity gauges. The type of instruments are there. Is many different instruments. So it is very important for you to classify the ones that you want to calibrate or do measurements with. Also, as I said, the current resources include reference standards, the personnel involved in the laboratory, procedures, and laboratory area. And within the laboratory area is also the conditions. Yes, you can see here at the bottom left the equipment. In the center, the equipment, but with these very nice people, handsome and attractive lady. This is the people that work at the pressure lab at CINAM, which is the national laboratory in Mexico, and also procedures. But definitely the most important part of a laboratory is people. You cannot work without the best people, motivated, knowledgeable, and qualified. Second step is to analyze the current state and do the pressure laboratory initial study. The initial survey should include at least three integrated aspects. A, current calibration and measurement capabilities. B, these CMCs, but the desired or potential customer requires. What I mean with this is where we would like to stand in the future, or we would like to have a more competitive laboratory. Then we have to know which type of customers we would like to have in the future. And C, current quality infrastructure. And you have the desired calibration and measurement capabilities, measurement value chain or calibration to be carried out internally in the company, including its clients or potential clients, as I said before. Regulations, technical standardization, accreditation, and conformity assessments is very important. And also the quality systems, which for a metrological pressure laboratory, it's normally ISO 9001 or ISO 17025. Also, this second step, which is to analyze the current state, we have to use the 5 M's, which is the base for any quality system. What is this 5 M's? Many of you already know, but I just go through it anyway. The first step is machinery, or measuring instruments for us in a pressure laboratory. The second one is the manpower. As I said, the most important part is personnel. This manpower is who is working in the laboratory, including not only his studies and experience, but his abilities. What is he capable or she capable to perform in this laboratory? Also, the manual of procedures or all the methods that we use, are they based in standards, written standards, or are developed by the laboratory? So we have to think about it and know if we have to do some other experiments to be sure that the methods used are strong enough. Also, very important is measuring conditions or environmental conditions, which include temperature, humidity, and also the space, and also the working tables, the whole area which we use to do measurements and calibrations. And also very important, the manual of quality system. This is the assurance that all we do will be done the same way always. Of course, improving each time that we can do it. Step number 3, to establish ideal future goals. It is important for the laboratory when we do the gap analysis to look at where we want to go or what we want to achieve later on. So can be laboratory recognized within the company, that is ISO 9001, or accredited laboratory. Or if we have an accredited laboratory and with international recognition. With all of this, we have to look at all the requirements according to the rules, local, national, or international, that may apply. We'll go to the step 4. As we can remember, there were 4.A. 4.A is to compare the current state with the desired goal, and the first part is to evaluate general requirements. This evaluation in a pressure laboratory begins with the review of the formal organization, appointment of technical managers and quality manager, as well as management of the documents of the laboratory. It is also necessary that all personnel comply with the training and qualification requirements according to ISO 17025, and those in the case that the laboratory is accredited, and those of the accreditation system. The calibration laboratory must ensure that all requirements for equipment, including those used for monitor and record environmental conditions, are met. I mean, we saw just before the 5 M's. This is just a reminder. Unfortunately, I don't have the whole time to talk about all the points, but you have to take the 5 M's as a base for this gap analysis. We continue in the general requirements, and as I said, the equipment, it's very important, but can be controlled very easily if we record all the maintenance requirements, we look at the measurement traceability requirements, and the calibration of reference standards is performed on time with traceability to national standards. I am sure that you all know that in India is NPLI, which is a very recognized laboratory worldwide. So please do have traceability to NPLI. The last point is especially important in the early years, because you have to record the drift of your standards use, and it is very well recommended in the world the use of the ISO standard 10012. We move to the 4.B, which is the comparison by means of the Ishikawa diagram. The Ishikawa diagram is the cause and effect, and we can put 6 points there. The first point, we can use measuring instruments. Second point, manpower. Third point, the method. 4 point, environmental conditions. 5th point, quality system. And 6 point, potential customers are under requirements. Then, for each of these points, we should add as much specific information as possible. And all of this, the idea is that we can increase or improve our CMCs. We move to 4.C, which is the comparison made by the SWOT analysis. The SWOT analysis is strengths, weakness, opportunities, and threats. And it can be internal, external. Some of them are helpful and some of them are harmful. So some of examples, for instance, the strength internal can be the number of metrologists. That is, we have a big number of metrologists with a lot of experience. That is our strength. One weakness internal could be that we have a good number of metrologists, but they don't have an homogeneous training. That is, some of them can only make measurements on manometers, and some of them can do calibration with pressure balances. Then we can also see at the external helpful points or opportunities. And one could become the reference laboratory of the company. Perhaps we have a maintenance laboratory which can improve to become a measurement laboratory, and then become a calibration laboratory, and become the reference for the whole company. That's external to the laboratory. Be aware that when we speak about external, it's external to the group. Could be external to the company.
Be Dr. George. Hello, Dr. George, can you listen me? Dr. George, can you listen me? I think he's not online.
Paper देना मैं paper paper देंगे
वो क्या
recorded
वो आए थे पहले उन्होंने बोला था so is it
हाँ मैम offline है ठीक है मैम
Thank you so much. So in this particular session, we had 4 presentations, excellent presentations. I thank all the presentees. I thank you for them for coming and giving the very good talk and giving their time here. So the next talk, next talk will not be online. So I request all the NPL people to come and join in the auditorium. The next talk by Dr. D.K. Svalsa is not going to be online. I request all of you to come to the auditorium, please. All the scientists and the students are requested to come to the auditorium, please. The talk will start right at 6 p.m. Please start immediately. नहीं सर वो बड़ी इंडियन स्टैंडर्ड टाइम वहाँ पे 18:01 दिखा रहा है हाँ तो मैंने बोला ना 6 PM पे होगी
मैम ने कैमरा दिख रहा है स्पीकर ऑन है क्या
आप ऑनलाइन बंद कर दीजिए लिंक बंद कर दीजिए
ठीक है
ऑनलाइन लिंक बंद कर दीजिए कैसे बंद होगा सेशन में आप कहाँ से
पूरा क्लोज करना पड़ेगा
भी देख रहा है वो किसी को किसी फोटो के लिए नहीं मिलते आप कहाँ थे आप सारे तो
आपसे को फोन लग गया है आपसे को फोन लैंडिंग बंद